Hello again. It's Jolly. You're going to get so tired of me saying that. All right, let's continue our discussion with radicals. So, the first lecture was talking about their stabilities. Now, let's talk about how in the world do you make them? Go back to our handout. Okay, so the radical reaction pathways. How in the world are we going to make those reactions or those radicals in the first place? Now, we've seen quite a few ways to make, positives and negatives to make carbanions and carbocations, to make nucleophiles, so forth. But how in the world do you make radicals? Now, these, remember, are highly reactive species, and so it's going to take, some unique conditions. All right, so there's three steps here. First of all, we have to create them. Okay, that's initiation. And then if they react together to make more of themselves, that's called propagation. And then if they eliminate themselves, it's going to be called termination. All right, so initiation. You'll always know, at least from my perspective, when I'm trying to get you to do radicals because there's going to be some unique conditions. All right, now heat is not unique, but this is like in the 400 degrees. Again, not all reactions need that high, but if I ever put 400 degrees, 300 degrees, etc., okay, I'm talking, hey, I'm supposed to be making a radical. So that's called thermal decomposition because it's using heat. All right, photolysis basically just means light. And so you could put a wavelength, or I tend to like to just put h nu. Remember, that stands for energy of light, or you could just write the word light, but that will actually break the bonds just as easily, especially in the upper atmosphere. All right, another way is a redox reaction. Now, peroxides are very special species. Okay, fairly weak bond. Okay, so if we were to go up to the top, we can look up their number. Okay, but that will break. And now I have two pieces that will get the radical reaction going. Okay, so that's a starting phase or an initiation phase is using some kind of a peroxide. Now, the peroxide is a redox reaction, and it does have to have a little boost, a little bit of light, a little bit of heat to get that going, but it starts with some very nice radicals that will react. All right, now I notice I said photolysis above, and I also put ionizing radiation. And so these are your high energy up in the atmospheres, your alpha particles, your beta particles, your gamma, your X-rays, things like that. Now in the laboratory, of course, we don't use those. But remember, a lot of the radical chemistry that's really interesting occurs in the upper atmosphere, and that's cosmic radiation. And then we could also produce them using electrochemical means. We don't in our discussions, but it's another way. Okay, so it's kind of a small list, but those are ways that we can start the initiation phase. All right, so what can be broken to create those? Well, we learned that the peroxides are pretty easy to break. H, okay, the halogen, so I'm just going to put an X. Okay, those were fairly easy to break. If you wanted to come up with a prediction, you would go up to your stability chart or your bond dissociation chart, and you could predict, hey, which bond in this molecule is more likely going to break first. Okay, so that's how you would determine which one would be the initiation phase. All right, what about the propagation phase? Well, the propagation means you already have a radical, and we're going to be making another radical. So let's just do substitution. So let's say I already have this radical. Well, it will react with something else. Okay, so let's say we have an HCl. Remember, for the curly arrow, we use the arrow with one side to indicate that we're only doing one electron. Okay, I substituted the radical for the hydrogen and then the hydrogen for a radical for the chlorine. And so that is a generic substitution. reaction for radicals. All right. Am I going to talk about the stability right there? No, that's just a propagation step. And another one, addition, just as you're expecting, is going to have to use a pi bond. So let's say this chlorine comes along and it's next to a pi bond. The key is I still have a radical. So propagation steps do not get rid of the radicals. They can just transfer them between species in two basic ways. They can either substitute or they can break pi bonds and they can do addition. All right, so there's propagation. Termination has a little bit more interesting variations. Okay, so termination is a reaction in which radicals are used up and none are produced. Okay, so I'm trying to get rid of these radicals. And how am I going to get rid of these radicals? Well, I could just combine them. Okay, so that's the easiest, simplest vision. Let's say we have that plus that. Oh, look, a radical and a radical combined together. No more radical. Okay, and I'm going to talk about the combination in more depth here in a moment, but just basically combine the silly things. Now, disproportionation is a hydrogen extraction followed by the radical recombination to form a pi bond. Now, that is a mouthful, but what we would do here is, let's say we had this radical, and then we had uh, how to draw it in this tiny space. Yeah. All right. So in disproportionation, this will rip off a hydrogen. Ah, but notice there's already a radical on this species. So these two radicals are going to go back and form a pi bond. So we get C, 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 there's the hydrogen I ripped off, plus C, C, C. Okay, so kind of a backwards propagation step. All right, so those are the two types of termination. Oh man, jolly, really? Look at all those examples for the combination termination. All right, we know that they're highly reactive species and they can do some very amazing chemistry, but you have to be able to get rid of them in the end. So, how are we going to be able to do that? Okay, so the interaction with impurities and/or here's a term, inhibitors or scavengers. Okay, so we're going to use species that want to eat up those extra radicals because we want to create stable radicals or at least persistent radicals. Okay, so stable, there's only two answers in organic chemistry, sterics and electronics. So we can either create one because it's sterically hindered, which means that radical is hard to react because it's so bulky, or we can make one that's electronically stable, or even better, we could just get rid of the radical in the first place. So what are we going to use as the radical sponges or these inhibitors? Well, of course, diatomic oxygen. Okay, is an amazing species because guess what? There's a pi bond and you will make the diradical. So in the atmosphere especially, diatomic oxygen is an amazing one that can help us out. All right, well, what else? Not so good in the upper atmosphere, but we could use NO. We could make one radical on each piece. Oh, so it would break one of the pi bonds. All right, what about conjugated systems? Okay, conjugated systems, remember, are very stable, and so conjugated systems are an amazing way to do this. And let me see, who do I list first? Phenols. All right, a phenol, we'd look at the top. What is our weakest bond? And it would be this one right here. Oh, look, there's an extra radical, and so the phenol donates that hydrogen in, and it creates that radical. Anything that stabilizes it. Okay, so how many different resonance structures can we draw for this radical? All right, well, let's try. Let's do that one. Let me see. Da, da, da. So there you are. And then it's going to go around. This should probably be looking familiar. And it'll look really familiar this semester because we're going to do it over and over and over. So let me see, where did that double bond go? That double bond went there. There's one there. There's a radical. It's going to happen again. And one last time. Okay, so we're going to find the phenoxide. Okay, so it's not negatively charged, but the phenyl has an O on it. So from phenol, we can create a very stable byproduct, and we have a natural radical sponge. And we'll see this, throughout nature. All right. So there's your conjugated systems. Okay. So anything with a conjugated system, just a reminder, that means every atom in a row has a p orbital. All right. Are there others? Yes. Nitrobenzene. We've got some butylated hydroxytoluene. Oh, huh. That sounds familiar. BHT. All right. There's our synthetic ones. Those are your preservatives. And DPPH, which is diphenylpicryl. I probably said that wrong. Hydrazine. Okay, there's lots of ones that are going to use these characteristics, but we're going to call phenol the nature sponge. All right, well, there's other things in nature too. Yeah, a lot of them contain my phenol group, but we call them the antioxidants. Okay, so the water soluble is ascorbic acid, glutathione, lipoic acid, uric acid, the carotenes, specifically beta carotene, and retinol. Okay, vitamin A. And if it's lipid or fat soluble, oh, the tocopherols, which is vitamin E, okay, and coenzyme Q, and I don't even know how to pronounce that correctly, ubiquinol. The key is they have to have something in there that will, act as the radical sponge. All right, there's a whole biological section at the end, so we'll talk about those structures later. But in a nutshell, you have to have initiation, you have to have propagation, and you have to have termination. If you want to know how much energy it takes, we of course would go to the numbers. And then I have some wonderful questions for you. For each of the following, show the indicated pathway. So for initiation, I want the thermal decomposition of diatomic bromine. So what I'm asking you to do is this. Oh, look, thermal decomposition, it can make two Br radicals. How about the photolysis of a peroxide? And I keep writing them underneath the reaction arrow. You could put them on top if you wanted. Okay, so I just give you a few examples of, hey, can you just show me initiation? Oh, you know what? Let's do this one. Propagation, a bromine radical with a hydrogen extraction of propane. Okay, so for propagation, I better end up with a radical for propane. Okay, I have a question. Should I rip off this one Or should I rip off this one? All right, if we go up to the numbers, our numbers would say that this one is the more stable. Okay, now I didn't specifically say which one in this question, but that's how you'd answer it. All right, and it's going to go down. We're going to be left with a secondary radical and some HBr. Wait a second, you just made a strong acid. Okay, the radical world is highly reactive, so I'm okay with that. All right, so there's some questions for you to play with on those. All right, initiation, propagation, termination. Until next time, Jolly out.